Amar, and today I'll be presenting my Lab 4 report on bar magnets for Physics 2212. The purpose of this lab was to measure how the magnetic field of a bar magnet depends on distance and then compare those measurements to the theoretical prediction given by the equations for on-axis and off-axis magnetic dipole fields derived by the Biot-Savart law. As a preview of my results, my log regression gave a slope of negative 2.28, and I calculated a magnetic dipole moment of 1.45 ampere meters squared. Okay, so the three main concepts behind this lab. First, we have the Biot-Savart law, which describes how moving charges produce magnetic fields. Second, the magnetic field of a dipole is given by the formula below, and which tells us basically how the field at any point in space around a dipole is. And third, we have the distance dependence form, where we write the field magnitude as k times r to the power n and take the natural log of both sides to get a linear equation we can fit with the regression. The first two equations are used in our GlowScript code, and the last two are used when we are doing our data. Okay, so for the experiment, I used my phone's magnetometer as a field sensor. The key steps were first rotating the phone so the magnetometer was orthogonal to the Earth's magnetic field to minimize interference. Second, locating exactly where the magnetometer chip sits on the phone. And third, carefully measuring the distance between the magnetometer and the bar magnet for both the on and off axis configurations. The system was a bar magnet and the surroundings were everything else. So here's my on-axis data. I took 3 measurements at 5 distances, and I averaged the distances and the field values for each group and plotted ln of bx versus ln of r. This trend line gave me the equation y equals negative 2.28x minus 15.053, where the slope is n and the y-intercept is ln of k. Where did we get the equation to graph this? Well, it was just the equation in our dependence law. Okay, so calculations. Using the y-intercept from the regression, I calculated k by taking e to the power negative 15.053, which gives 2.9 times 10 to the negative 7. Then, since on the axis of a dipole, the field equals mu naught of 4 pi times 2 mu over r cubed, I solved for the magnetic dipole moment mu, getting 1.451 ampere meters squared. The value was then used as the input for the GlowScript simulation. Okay, so for off-field data, I placed the magnetometer at 45 degrees from the magnet's axis. I took 3 measurements with d-perp values of 7.58 and 7.75 centimeters, giving an average d-perp of 7.75 centimeters and average total distance around 10.96 centimeters. After correcting for Earth's field and computing the net field of all 3 components, the average measured magnitude was 3.22 times 10 to the negative 4 Tesla. Okay, so for observations, in terms of qualitative observations, when the magnetometer was far from the magnet, the x component of the field was close to 0, and as it moved closer, the x component increased consistently, which matched what the dipole model predicts. The field gets stronger at shorter distances. Okay, so here was our computational model. For initial conditions, I had the physical constant mu naught over 4 pi, which creates a magnet as a cylinder at the origin, and set mu mag to 1.45055, which is what we got from calculations. Okay. The second part, the rest of the code, sets up the observation locations, 2 on axis and 4 perpendicular, computes a field at each using dipole B, and draws colored arrows. The orange represents on-axis field, and the cyan represents the perpendicular field. Okay, so here are our results. The on-axis field came out to 3.63 times 10 to the negative 5 Tesla, in the x direction at a distance of 0.2 meters. The perpendicular field was negative 1.81 times 10 to the negative 5, which is exactly half the on-axis value, consistent with the dipole formula. The computed field at 45 degrees had a magnitude around 1.74 times 10 to the negative 4 Tesla. So some similarities and differences. My measured off-axis net field was 3.22 times 10 to the negative 4 Tesla, with a computational model predicting 1.74 times 10 to the negative 4 Tesla. There's a factor around 1.85 between them, and so what are some assumption errors that led to this? Well, assumptions were that the bar magnet acts as a magnetic dipole, and the magnetic field falls off as distance increases. And the errors were that nearby metallic or magnetic objects could have distorted the field, and uncertainty in pinpointing the exact location could have led to some precision errors. Okay, so discussion. What if you hadn't oriented your experiment to compensate for the magnetic north and instead laid out your meter stick at some intermediate angle? Well, the Earth's field would have added to or subtracted from the bar magnet's field depending on orientation, which would have skewed all my measurements. And for the second question, if I stuck 2 identical magnets together end to end, the dipole moment would have effectively doubled, so the field strength would double.